so we are wrapping up the notes from 1-4. There. Nice. Okay, we're in business. Okie dokie. Alright, so we are on page 4. Okay, so how would I, just sort of a quick refresher, how would I look at a graph and see, in quotation marks, see a horizontal asymptote? You're thinking vertical, horizontal. How would I look at a graph and visually check, remember these right here, and kind of look for, but the dotted line won't show up on like this graphing calculator. Yes. Okay, so your graph is leveling out to some value. So you've got this leveling out, a leveling out. So visually that's going to indicate to you that you have a horizontal asymptote. The vertical asymptote will be that break in the graph. So like from left to right, there will be a break. Left to right, you've got that choppy little break. Choppy little break. And those are coming from what makes your denominator 0. Okay, so it turns out we can identify a horizontal asymptote without doing anything. Graphing it, looking at our table on our calculator, we can analyze the function and determine if it will have a horizontal asymptote, and if it does, what is it? Okay, very cool. All right, so to determine a horizontal asymptote, or sometimes there might be multiple ones, evaluate the highest degree term in both the numerator and denominator as x approaches infinity and negative infinity. Okay, so why is that? Remember the definition of a horizontal asymptote is there is a line that's a horizontal asymptote for a function if the y approaches that number as x approaches infinity or negative infinity. Okay, I want you to go back and look at this graph here. Imagine that the x is getting bigger and bigger and bigger. The denominator is going to get bigger and bigger and bigger, right? Is the numerator changing? No, it's 4. So you're going to have 4 over a bigger and bigger and bigger number. What's going to eventually happen to that fraction as only the denominator is getting bigger? It's getting smaller. And it will get closer to what number? 0. That was our horizontal asymptote. So I can analytically look at that and say, okay, only that denominator is getting bigger, therefore those fractions are going to get smaller and closer to 0. Okay, look at this one. Same thing with this fraction here. Only the denominator is getting bigger as x gets bigger. Okay, there's a negative out front. Okay, so this whole fraction here is going to get closer to 0. Negative 0 doesn't mean anything, right? So it's still 0. And then if I subtract 3 from 0, guess what my horizontal asymptote was? Negative 3. Cool. Does it always work that way? Oh, what would I do with this one? Okay, so that's what the little thing that I just read is saying. If I have a variable at top, I have to evaluate both x's getting bigger and bigger and bigger. Okay, so this is very conceptual, very abstract. But we're going to imagine that x here and x here is continually getting bigger. When x is like 10,000, how important are the 1 and 2 here? So insignificant. So roughly, the numerator and denominator are becoming the same number. And what would that whole fraction's value be? Very close to 1. Guess what our horizontal asymptote was? 1. So basically the numerator and denominator are becoming the same number. Okay, yes, you have this -1 and -2, but think of x being 1,000,000, 10,000,000, 10 billion, like -1, -2, that doesn't make a difference. So basically your numerator and denominator are almost the same number. And anytime you divide a number by itself, you get 1. With the exceptions. Okay, so we're going to look at these and just determine what they're going to be. Then I'll show you how to use the table, and then we'll check on our graphing calculator to see if we actually see that asymptote. Okay, so I have highest degree in the numerator. I have variables top and bottom. My highest degree is x squared. My highest degree down here is x to the 4. These plus ones and minus ones as x gets super big are totally insignificant. So if I just evaluate 8x squared over x to the 4, what does that reduce to? 8 over x squared. Okay, so that's kind of the sum effect here. Got 8 over x squared. Only x is getting bigger. 8's not changing. So that denominator is very quickly getting very large. So that whole fraction is getting smaller and closer to what number? 0. So the horizontal asymptote here is y equals 0. Because this thing is approaching 0 as x is getting bigger. Okay, what if x gets bigger in the negative direction? Well, I'm squaring it. So it's still just going to be a big positive number under there. 8 over a bigger and bigger and bigger number gets closer and closer to 0. Okay, look at this one. Highest degree term, like the term that's sort of controlling the numerator, is 2x cubed. Highest degree term on the bottom that's kind of in control of the denominator is x squared. Okay, if I reduce that, I get 2x. Tell me what happens to 2x as x gets bigger and bigger and bigger. It gets bigger and bigger and bigger. Okay, what if x is negative here? Then 2x gets further and further negative, correct? So do I have an asymptote? Am I approaching a number? No. No horizontal asymptote. Because this quantity just kept getting bigger. It didn't start approaching a number like this fraction starts to approach 0 as x gets bigger. This one just gets bigger. Okay, and in a minute we'll look at the graph and see what that means. Okay, next one. Highest degree term is 4x squared. Highest degree term is 2x squared. So those are kind of controlling the numerator and denominator. They're the dominant terms there. If I reduce that, what does that become? 2. So look at this. That tells me that no matter what I sub in for x, this fraction is just pretty much going to be 2. Guess what my horizontal asymptote is? 2. So if this evaluation as x gets bigger approaches a number, that number is your horizontal asymptote. If it doesn't approach a number, you don't have one. So this is horizontal asymptote at y equals 2. So we can actually get a lot of information before we even try to graph it. Okay, let's go back and just examine these on the calculator. So let's go back. Y equals, clear out whatever you have there. Remember, alpha y equals gets you your fraction. Does anyone have a calculator that doesn't do the fraction? Okay. Or if you just don't want to use the fraction, then you put the entire numerator in parentheses divided by entire denominator in parentheses. Now you need help. Okay, hit graph. Who doesn't have a calculator on their desk? The graphing one. Just Kaylee? Do you have one? You need one? Anyone else need one?
Can you grab me one as well, please?
Kaylee. Oh, wow. This one looks weird, doesn't it? This little, like, caret button under the clear. So you do raise to the 4. And then do a right arrow so it'll get out of the X button. Uh-huh. do Zoom standard, Zoom 6. Tell me if that doesn't help. Anybody else have a question about the calculator? Okay. Do we see a horizontal asymptote at y equals 0? Yeah. Okay, but what about this? This is going down to negative infinity. Remember, in the middle, it doesn't matter. Horizontal asymptote, we're looking out far to the right, far to the left. Is the graph leveling out? And that answer is yes. And it's leveling out onto the x-axis, which is the equation y equals 0. How many vertical asymptotes does this have? 2. Can you see 2 vertical breaks in this graph? Okay, so let's just quickly go back and look at that denominator. That tells me that there are 2 values that will make that denominator 0. So at both of those values, I'm seeing vertical asymptotes. What are those 2 values that will make that 0? -1 and +1. Okay. All right, let's graph this next one. See if we can visually see that there's no horizontal asymptote, that we were right. Okay, makes total sense. If I look out far to the right, far to the left side of that graph, there's no leveling out going on. Over here, it's going up to positive infinity. Over here, down to negative infinity. No horizontal asymptote. And this doesn't even appear to have a vertical asymptote, does it? Okay, and look at the denominator. This is maybe the last denominator we did yesterday was like that. There's nothing that will make that 0. Therefore, I'm not seeing any vertical asymptotes. Okay, last one. This one was going to be at y equals 2. So let's double check that. And then I'll mention, oops, gotta go to y equals. Now we're in business. Very clearly leveling out going on there, right? To the right, to the left. It's not on the x-axis. I know already because algebraically we figured out that it was a 2. But what was that trick I showed you yesterday? That we could use the table to see what it was going to way out to the right or left. Remember doing that? We went to table set. And I just started the table at a really big number, or I could do a really small number. I can do -100. And then I did my table change. You could go by 10s, 100s, 50s, just something kind of large. And then we'll view that table. I hate when it gives me decimals. I mean fractions. Here's some decimals. Okay, then it will. So 1.94, 1.94. Lord only knows what that fraction equals there, but so you can see that they are close to 2. Let's see. Table set. Let's try negative. What am I doing? Let's try that. Okay. Yep. I started at a bigger number, -10,000, I think, on that. And those are very clearly close to 2. So that's how you can check a table for horizontal asymptote. Just start it at something really big or really big in the negative direction and examine the decimals or evaluate it algebraically. Question. Okay, so as we have seen from the examples, a rational function will never cross a vertical asymptote. And that's because those values that create a vertical asymptote are undefined in the graph or in the function. But a rational function may cross a horizontal asymptote. Let me show you one. go to your y equals. I want to show you one because we haven't done this, but I want to show you one that actually crosses the horizontal asymptote, but it still has an asymptote. Okay, we're going to make a fraction, and we're going to put x over sine x. Okay, sine is 2 buttons above 7. X over sine x. Oops, I got that backwards. I think I want sine x. Well, let's just see what this looks like. I think I have it backwards. Oh yeah, definitely. Okay, this one's cool too. Very nice. What's that even look like? It looks like the monster's teeth. Snaggly monster teeth. I don't know. It's kind of cool. How many vertical asymptotes do you see since we're looking at it? Multiple. How about that? Multiple breaks. I'd say there's probably one over here, 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 probably one over here. And if I expanded that window view, I'd probably see more. Okay, let's go back, because that is not what I wanted to. Go back to y equals. Let's put sine x on top and just x on the bottom. Those of you who take AP Calc will examine this one again next semester. We're going to change something as soon as this finishes. Okay, let's go to mode. Find your mode button next to the second button. Find where it says radian and push enter. Radian, push enter, and now hit graph. Y'all will know what that means so very soon. What the heck? Okay. Let's do zoom trig. Zoom 7. I had a good idea. It's just not playing out. There we go. That's good enough. Okay, so I did zoom trig because that was a trig equation, so it's setting up a better window for me for this equation. Okay, so, gosh, how would you describe this? I'll tell you, one of my AP Calc classes years ago called this the Squidward graph. No, it was Paul Robinson's grade, Kaylin Smith, and that whole crew. Because of Squidward, there was a dancing Squidward. You know what I'm talking about? And so his little arms, but they were like, that looks like Squidward. So that has since been called Squidward graph. Okay, so what is happening? Just watch my calculator. You don't have to do anything on yours. I'm going to change this and this. While this is graphing, is there any symmetry in this graph? What kind? It's symmetric about the y-axis. This would have y-axis symmetry, which is also then called an even function, just FYI for the fun of it. Okay, so what this graph is doing, as I go farther out, it's flattening out. So you've got these little hills that are just sort of mellowing out as it goes along. Okay, well look far to the right, far to the left. Is it leveling out? It is. On what line? The x-axis. Even though, here's a good word, y'all, even though it's oscillating over and above the x-axis. Good word, right? Like an oscillating fan, it goes back and forth. So this graph is oscillating over the x and y x-axis. And as we go to the right and to the left, it's kind of flattening. It's like just getting sleepy. So I do have a horizontal asymptote at 0, but it keeps crossing it. But that's okay. Vertical asymptotes, you will never see that happen. Graph will not cross a vertical may occasionally run into a function that crosses a horizontal asymptote. Okay, just a little fun there. A little math fun for the Friday. All right, here we go. Example 6. Math fun Friday. Y'all wouldn't be here if you didn't like math, right?
I'm legally required.
Oh, there's nowhere else you would rather be, Max.
That is honestly 100% true.
I know.
I'd rather be in this classroom than you need. That's not technically a classroom.
All right, example 6, guys. Shh. All right, remember from lesson 1-2, what makes the denominator 0 and thus makes the function undefined does not always result in a vertical asymptote. Do you remember when we graphed something and it had a hole in it? Okay. While it will always be an undefined domain value, sometimes it appears on the graph as a hole in the graph. This happens when there is a common factor in the numerator and denominator. Okay, so let's look at this function here. X squared minus 1 is a difference of 2 squares, and it does factor. X plus 1, X minus 1 are our factors, and then I have a denominator of X plus 1. So I have common factors there that will cancel. X plus 1s will cancel. All right, so what is going to happen is this graph is going to look like y equals x minus 1. What is that graph? Linear. It's a line, a y-intercept of -1 and a slope of 1. So when I graph this rational function, it's going to look like a line. But look at your denominator. What value makes the function undefined? -1 creates a 0 in the denominator. Okay, so what is our domain here? All real numbers except -1. The easiest way to say that is x can't be -1. Okay, but a fancier way to say that would be x can be -infinity to -1 union -1 to infinity. That means everything except we're going to jump over -1. Okay, so we already factored and simplified, so we've taken care of that. All right, so let's graph it. So I'm going to go to -1 for my y-intercept, and my slope is 1. Don't connect the dots yet. Okay, so that one value that I can't use is at -1. So I'm going to go to x equals -1, trace it to where it would be on the graph, place that hole in the graph, then connect everything else. Now, if I showed you that, you wouldn't automatically think, oh, that's a rational function there. Like, there's no vertical asymptote. This one certainly doesn't have a horizontal asymptote. But it did start out as a rational function. So this is kind of like a cool little exception where it looks like a line with a hole in it. Question? So every little thing that makes our denominator 0 is not going to be a vertical asymptote, but it will always be undefined. It can appear as a hole in the graph. Are we okay? All right. There's a third type of asymptote. It is called a slant asymptote. Guess what it looks like? A slanted line. These occur when the degree of the numerator is exactly 1 greater than that of the denominator. For example, this one right here. X cubed plus 1 over x squared. Degree of numerator is 1 more than degree of denominator. It does have a horizontal does not have a horizontal asymptote because the degree in the numerator is larger than the degree in the denominator. As x approaches infinity, all right, so let's evaluate this degree over degree. Highest degree over highest degree. What does that reduce to? Just x. As x gets bigger, what's going to happen to y? It's going to get bigger, so it's going to approach infinity. What about as x gets closer to negative infinity? Then y is going to get closer to negative infinity because this fraction reduced to whatever x is. Okay, so we're going to check out what this thing looks like and see if we can see a slant asymptote. All right, go to y equals, get our fraction set up, x cubed plus 1 over x squared. Prepare to be amazed. That looks different, doesn't it? Do you see a vertical asymptote? Yeah, appears to be one at x equals 0. But also, can you see, and we're actually going to graph in a minute, so you'll definitely see it, but can you tell that there's a diagonal line that these both ends are approaching? Okay, there's our slant asymptote. So it has a vertical one and a slant one. Why is the vertical one there? Look at your denominator. What makes it 0? 0. Doesn't cancel with any factors up here, so I'll have that vertical asymptote. How do I find this slant asymptote? Well, funny you should ask, because the way to find it is by using division. So long division. Synthetic, if that's a possibility, but it's generally going to be long division. If I'm dividing this by this and I'm dividing by x squared, I have to use long division there. Okay, so we're going to divide the numerator by the denominator. If there's a remainder, we'll ignore it, and I'll show you why in just a sec. Okay, so let's find the slant asymptote. So I'm going to take x cubed plus 1 and divide it by x squared. These are generally very short, sweet and short here. What's x cubed divided by x squared? X goes up on top. X times x squared is x cubed. Subtract. That's gone. Bring down a 1. That's a remainder. Okay, so technically I'm getting plus 1 over x squared. Now, remember, I'm letting x get super big. Well, if x gets super big, this fraction is super small and pretty much equal to 0. So that's why we ignore the remainder, because it's going to be super insignificant. So this right here that I just got, y equals x, that is my slant asymptote. Okay, now we're going to go onto our calculator and graph this line, and you can actually see that that's the line that it's approaching. So I'm going to add to my graph a second equation of y equals x. And if you do have a color graphing calculator, it is cool. You can use a different color, and then it sort of really pops. Look at that. I mean, it very clearly approaches that line. Isn't that cool? Who needs help? What's wrong?
So the answer we got from dividing, how do we get y%?
Other than that?
Like we got x plus 1 over x squared.
So that's a remainder. We ignore it. So just doesn't matter. And then y equals this is your slant asymptote. Just make it y equals whatever you got. The remainder? Because remember how we look at horizontal asymptotes is we look way out here as x is getting really big or really small. And if I plug a really big number into 1 over x squared, that's going to approach 0. So it's just not that significant as x gets bigger. So always when you get a numerical remainder, just ignore it. Just drop it from the problem. All right, question? Isn't that cool? All right, so we can have vertical asymptotes, horizontal asymptotes, slant asymptotes, and we can have holes in the graph. Who knew? So cool. Okay, find a slant asymptote of this. How do we know there will be one? Degree up top is exactly 1 higher than degree on the bottom. Could I use synthetic on this one? I could on this one. Do we want to?
Yes.
All right. What number goes in the box? 2. Remember, we take the opposite of it. All right, still, if there's a term missing, we need a 0, but that's not the case. 2x squared, negative 3x, 1. 2 comes down. Multiply, add, multiply, add. Okay, and remember, this was my remainder that I will ignore for this purpose. This is my constant and my x coefficient. So, my slant asymptote is y equals 2x plus 1. Ignore the remainder on these, not on your regular division problems, but for these we ignore the remainder. All right, shall we graph it? You want to see it? Seeing it is believing it. We've got 2x squared minus 3x plus 1 over x minus 2. Okay, now while you're in your y equals menu, go ahead and put your slant asymptote in there as well, so that we can see how it's approaching it. Ready? Hello? There we go. This thing is so slow. I wonder, I bet you there's another curve further up. Okay, so you can zoom out. I'm not a huge fan of zooming out because I don't think I need to see further out this way. So I'm going to go to my window and I want to see higher. That's all I want to change. So I'm going to change that y max. I'm going to try like 15. There it is. These are so slow. And there's the slant asymptote. Very nice. Question? All right, good stuff, good stuff. Okay, almost done, almost done. Quicker than yesterday. Okay, so I have... Well, last one, guys. I have a rational function graph here. I don't even have the equation for you. It's just here is a graph. And we're going to answer all these beautiful questions. Ready? As x approaches infinity, f of x, aka y, approaches what? We might have to do some guesstimating. I would say 2. It didn't quite look halfway, right? It's a little less, so we're going to have to make that approximation that that's 2. So as x is getting super big, that means way out here, what is y getting closer to? It appears to be 2. So we're going to make that determination that this is 2. It may be, I think it's 2. Okay. As x approaches negative infinity, that means way out over here, on the left-hand side of the graph, what is y approaching? Appears to be 2. Because you've got that same leveling out. You can see whatever this number is, we think it's 2. You've got a horizontal asymptote there. So on both ends of the graph, that's what your y values are approaching. Therefore, we do have a horizontal asymptote of y equals 2. Let's jump down to k and answer that. Horizontal asymptote is y equals 2. All right, what about as x approaches 4 from the left? What is y approaching? It appears to be negative 2. This is 5, so I think a safe assumption is that this is 4. So approaching from the left, I'm coming this way, and the y's are dropping lower and lower, so I would say negative infinity. What about as x approaches 4 from the right? What is y approaching? Positive infinity. What about as x approaches 4? Or either answer. Because they differ, we just say there's not a number we're approaching. They're not a value. Okay, the graph is increasing over the interval or intervals. Okay, so you probably haven't done this since Algebra 2. Imagine that we have a line, and we're going to move it across the graph from left to right, always from left to right. If you are walking, driving, running on this curve from left to right, where are you going uphill? Never. This is gradually getting lower, 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 quickly getting lower. Okay, then we start here. Remember, we're moving left to right. Downhill, 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 slowly downhill forever. So I'm never increasing. I'm never going uphill. Okay, so the graph is increasing over the intervals. None. It's never increasing. Where is the graph decreasing? So where are we going? Downhill as we move left to right. Everywhere except, where do we take a break? 4. Going downhill, downhill, downhill. Pick back up here, downhill, downhill, downhill. But I can't say all real numbers because I don't have a graph at 4. So I'm going to say this, negative infinity to 4. I'm going to use parentheses, that means don't include 4. Union, that means or together with 4 to infinity. And that's that interval notation that you used in Algebra 2. So I'm skipping over 4 because the parentheses mean don't include 4. If it included 4, then I would say all real numbers, or negative infinity to positive. Okay, what's my domain here? X cannot be 4. Or I can write the same exact thing here. So let's just do both. X cannot be 4 or negative infinity to 4 union 4 to infinity. So I have to indicate that I don't need to include 4. I have to skip over 4. And that's accomplished with this or this. What's my range? All real numbers? Do I have a y at 2? All real numbers except 2. So how would I write that? I can say y is not 2. That's the simplest way to say that. Or I can go negative infinity to 2. Parentheses means don't include 2. Union means add to the list. Combine with 2 to infinity. All right, the vertical asymptote is what? X equals 4. Horizontal asymptote, we already got that. Y equals 2. The 0 is between what two integers? What is the 0 on a graph? X-intercept. Okay, we're going to have to do a little approximating. We've said that this is 4. So what do you think that is going to be between? Let's see. I would say that that's probably 3 in the middle there. So yeah, I'd say between 3 and 4. We can't tell exactly what it is, but I think it's safe to say it's between 3 and 4. The y-intercept is between what two integers? Where's it crossing the y-axis there? You're just guessing between what and what? Between 1 and 2. Question. All right, let me get your homework. Oh dear, you've got 35 minutes to work on it. we can go to the restroom one at a time, please. Yep.